Here's a very interesting kinematics question, which tackles one misconception, which has to do with the relative velocity as seen from the perspective of an observer who is rotating. And if you'd like to see anything similar to this on the channel, or if you have any suggestions for topics or specific problems that you'd like to see, let me know in the comments. So let's read the problem and let's see how to approach this. So a stationary pole A is viewed by an observer P. Now this stationary pole A, we can actually think of it as a stationary observer instead. And we've got a second observer at P, who in this case could be a child that is on the merry-go-round. Now, this merry-go-round is rotating about a vertical axis with angular velocity capital omega. And what we're asked to do is to find the velocity of, so let's write it as the apparent velocity of A as seen by the observer at P. So this is what we have to find. And we also have to figure out whether this velocity, so is this velocity a function of the location of the observer on the merry-go-round. So let's say f of location like this. Okay. Now, before we answer any of those questions, what I would do instead is I would try to solve a different problem. I would try to find the velocity of the observer at P with respect to the stationary observer A. So I would instead find this first, and then I would find what the question is asking us to do, which is VA with respect to P. And then we're going to see if the two are the same. Because intuition tells us that the two should be the same. Because think about it this way. So let's say that you're on a road and there are two cars. So there are two cars approaching each other. Let's say this car is, let's say this car is stationary actually. Let's say this one has a velocity of 0, and let's say this car has a velocity going that way of maybe 15 meters per second. And let's say this is car A and this is car B. So if we're inside car A, we can tell that the velocity of car B with respect to car A would be, let's say, minus 15 times I meters per second. And I'm using minus because I'll consider everything going to the right as positive. Now, if we're inside car B, on the other hand, then the velocity of car A with respect to car B is going to be exactly the same, well, exactly the same magnitude, but it will be positive because if we're inside car B, we're going to see car A traveling towards us with 15 meters per second. So is this actually something that holds true even when you have a rotating coordinate system? And this is what we're going to try to answer, and this is why we're going to first attempt to find this instead. So let's first draw out the merry-go-round and the observer at point P once again. So let's say this is the center of the circle, which is B in this case, and then the observer is somewhere here. And let's say, let's give this an angle as well. Let's say that this angle is theta, and let's say that the observer at P is at a distance lowercase r away from the center, and we know that the merry-go-round is spinning with an angular velocity capital omega, which means that the velocity at P is given as capital omega cross r, which if we split those vectors into components, and what I'm actually doing here is I'm saying that this is my coordinate system, okay, and this is placed inside point B, but I'm not going to put it on the drawing because it's going to become a bit messy. So we have capital omega here, which is the, well, that's the k component and the only component of angular velocity. And then we have this, which is our sine theta, and that's our cos theta, and that's 0. Okay, so the determinant is there for I multiplied by, and we should have minus omega r cos theta plus j times, and we have omega r sine theta. Okay, so this is the velocity of point P. And if we want to find this in yellow, so that's the velocity of P with respect to A, okay, what we can write is, well, what we can do is apply Euler's equation for velocity, and this is how we can do that. I'll say that the velocity of P is equal to the velocity of A plus the relative velocity, which is what we're trying to find out, and then plus omega cross A P. Okay, so in other words, what I'm doing is I'm putting my coordinate system at point A. This should be y and this should be x. And I'm saying that the velocity of P is equal, the absolute velocity of P is equal to the absolute velocity of A plus the relative velocity plus this term, which has to do with the rotation of the coordinate system. But here's the thing. If we're at A, which is a stationary point, right? Is a stationary observer, then the coordinate system doesn't actually rotate. So this term here is 0, which means that the relative velocity is equal to Vp minus Va. And we also know that Va is stationary as well. So this cancels out, which means that whoever is at A will actually perceive the velocity of P as the absolute velocity of P, which makes sense, right? So that is, let me write it here, minus omega r, I think there was cosine of theta times I plus, and then capital omega r sine theta times j. Right, so for someone who is at point A, they will perceive the velocity of P as being equal to this, which, I mean, if you look at this expression, this definitely depends on the location of point P, right? Because this depends on how far away from the center point P is, because it depends on R, and it also depends on the angle theta as well. So for someone at point A, the velocity of P does depend on the location of point P. But now let's try to look at things the other way around. Let's try to write Euler's equation, but this time I'll write it like this. So the velocity of A is equal to the velocity of P plus the relative velocity. Now this is a different relative velocity than here, okay? And then plus, and this term is going to be omega cross, and then we have PA, right? And this term is due to the rotation of the coordinate axis of the merry-go-round, which is capital omega, and that's what the problem gives us. So what we can then write is the following. The relative velocity, which is what we'll try to obtain an expression of in the end, is equal to VA minus VP, and then minus omega cross PA. Okay. Now, one thing we can notice straight away is that this term vanishes because that's the velocity of the stationary observer, which by definition is 0. So the relative velocity is therefore equal to minus Vp, and then minus, we have capital omega cross Pa. Okay. Now, we also know what Vp is. So Vp, as we saw earlier, is omega cross r, but r is the same as vector bp. Okay, so this is omega cross vector bp, and then we have minus omega again cross vector PA. So an easy thing to do right now would be to factorize the omega. So this would be minus capital omega cross, and then brackets, and we have BP plus PA. So according to the rules of vector addition, BP plus PA, let's see what that is. So BP is this vector, PA is this vector, which means that BP plus PA is equal to BA. Okay, so this is minus capital omega cross BA like this. And we can now easily get an expression for this, which is minus, and then we have ijk, and then we have 0, 0, and omega, and then BA. BA is actually a constant, and it's the distance between the center of the merry-go-round and the stationary observer who is at A. So BA we can actually write as D, 0, and 0 because the question tells us that this distance is equal to D. So it has an X component only, and that's equal to D. Okay, so the relative velocity is equal to minus, and then we have omega d times j, and that's it. So this relative velocity of A with respect to point P is very different if we compare it to the velocity of P with respect to A. The velocity of P with respect to A, which is to say the velocity seen by someone at A, of point P, does depend on the location of point P on the merry-go-round. So it depends on how far away from the origin of the merry-go-round point P is. It depends on the angle theta. But have a look at this. So for someone who is on the merry-go-round, irrespective of where they are on the merry-go-round and irrespective of that angle theta, the velocity of point A, so someone who's at point B will see point A having this velocity. And this velocity doesn't depend on anything other than how fast the merry-go-round is spinning, and it also depends on that distance between the center of the merry-go-round and observer A. Okay, so it doesn't depend on where point P is located on merry-go-round, and it doesn't depend on the angle, it doesn't depend on the radius. So the only thing that matters is the angular velocity of the merry-go-round and this distance d. And that is what someone on the merry-go-round will see. So they would see point A moving in the negative y direction with this velocity. And that's the end of the question.